Hey everyone, welcome to another video. And today we're talking about a sample proportion um, and a bit of a different concept than what we've been doing so far. Because so far we've been looking at distributions and calculating probabilities. Um, Now we're going to be looking at calculating the probability of a certain proportion. So not the number of things like, not the number of successes that we've talked about before. So we might have talked about, given if we choose a random student from a population, what's the probability that they're taller than 185 centimeters, something like that. What we're going to look at now is sample proportion. And so what's the proportion of a certain thing? And so as an example, well, let's just go straight to this example that I've got in front of you. Let's say that we've got this big group of what do we say, tokens or whatever. We've got a bunch of tokens in here, okay? And let's say that that's my population, and let's say that there's 100 red tokens there and 300 black tokens there. Now there's not, right? Okay, but I just wanted to have the numbers there that were big enough for you to believe what I say, but small enough so that we sort of still understand the maths relatively easy, because this is a bit of a difficult concept, but the maths is relatively easy. So what we're going to do is so we've got 100 red tokens and 300 black tokens in there, okay? And so what we're talking about is we're sort of going to try to calculate P, right? And so what P is, and P is the proportion of, let's say P is the proportion of red tokens in this population, right? And so we would know that P is equal to 1/4, okay? Because there's 100 red tokens, 300 black tokens. So P, the proportion of red tokens is 1/4, 1/4. Um, but what we're going to do, right? What we're going to do is there's situations in life when we don't actually know what the P is, and so we need to sort of do some calculations, some way around it. The way that we approximate P is by finding P hat, right? And P hat is just a sample size of whatever, sample size N. And what we do is we choose a group of that. We take a sample of the population, and then we have a look at how many reds we have in that sample, right? And so let's say if I choose these three, right? Those three, how many of those are red? Well, that one would be 0 out of 3. Right, so the proportion, so 0 out of 3, that proportion would be 0. Or I might get, if I choose these three there, the proportion would be 2 out of 3. If I choose these, you get the picture, right? If I choose that picture there, then the proportion will be 1 out of 3. And just to finish it off, if I chose, just so you can see, if I chose those three, if it was a random sample and I chose those, it would be 3 out of 3. And they're all the possible outcomes that could happen there. It could be 0 out of 3, 1 out of 3, 2 out of 3, or 3 out of 3. And what we're seeing here is that what what I'm sort of describing here is very, very, very similar. We could talk about that X is the number of reds in the sample, right? So my sample size 3. So X is either 0 or 1 or 2 or 3. We've done that before with binomial, right? But this is a slightly different way of talking about. Instead of saying I got 3 reds in my sample, what we're saying now is that the proportion of reds in my sample was 2/3 or 1/3 or 3/3. So I hope that makes sense. But what we're saying, right, is that P hat, right? So P hat, I'll just write this here somewhere, that P hat is the distribution um, is the distribution of all the possible p hats that we get. So if I take, heaps and heaps of these samples of size 3 and I put it together as a distribution, and all that collection of little p hats is equal to this distribution capital P hat there. Okay, so I hope that makes sense. And just to sort of outline this, right? So if I put those results into a table, right? And I calculate some probability. What's the probability? I'm just looking at this table here, right? So if X is the number of reds, what did I say, reds? Yeah, X is the number of reds that I got in my sample of size 3. Then I could calculate my probability. So maybe I'm just throwing numbers here. It really doesn't matter, right? So 0.4, 0.3. What's that? 7, 9, 0.1. Right. Let's say that there were the probabilities of getting 0 reds, 1 red, 2 reds, and 3 reds. If I down the bottom, I'll do my p hat. Remember, that's like 0 out of 3. That's like 1 out of 3, and that's 2/3. and that's 3/3. And of course, 3/3 is 1, and 0/3 is just 0. And so you can see how there's this really tight link between p hat and x. And what is that tight link? The tight link is just that p hat is just is the same thing as the distribution of x, but we're just dividing by n. Here, we do all of these. Can you see we've got 3 here and 3 here? Got 2 there and 2 there, 1 there, etc., etc., etc. That's the link, but we're just dividing by n each time. So that's the only difference between x and p hat. Is that we've got x over n. And that's sort of how we convert between the distribution of p hat and x, all right, where x is the number of reds and p hat is the proportion of reds in your sample. I hope that sort of makes sense. We'll do an example and it sort of hopefully will come a bit clearer. We've got our expected value and variance and standard deviation as per normal. I won't go through these painstakingly, but just to have a think about this. What's the expected value of p hat? What do you expect to happen? Well, you would expect to get the same proportion in your sample that you would from the population. So our population was 1/4. So the probability that you get a red is 1/4. And so it makes sense that what we expect to get for p hat is p. Okay, so that's why the expected value of p hat is p. The variance there, again, we're just dividing by n because just like we said here, dividing by n to find p hat. So the variance also divides by n. And the standard deviation, as per normal, is just the square root of the variance. Okay, so a couple of helpful things in there that we'll use in this next example. So let's have a look at this, right? So you've got a forest. 1/5 of the animals in a forest are known to be deer, right? So we've got this forest, and 1/5 of those animals in that forest are deer. We take a sample of 20 animals and let p hat equal to the distribution of the random variable. It's a tongue twister of the sample proportion of deer. So all it is p hat is just the collection of samples. So we're taking 20 animals. And it was saying what's the proportion of deer in that sample. I meant to delete that. Sorry, I just get that out of the way because I added a question to it, so just disregard that. Just getting rid of that. Silly me. All right. So let's have a look at this. So part A wants us to find the probability that p hat is greater than 1/4. All right. Now, if you've sort of understood what I've sort of said so far, you might even be able to figure out, oh, this is just actually a really simple question. And it kind of is. I'll show you sort of how to go about doing this. And then we'll sort of look at what's the shortcut here without sort of having to do much maths. Okay, so we want the probability that p hat is greater than 1/4. Now we set up here that p hat is equal to x over n, all right? So this probability is actually equal to, I'm saving a space bar, saving a bit of space here. So p hat is x over n. So I'm just replacing that. I'm just getting rid of the p hat and just going to an x distribution. And what I'm essentially saying here is let x be equal to the number of deer in the sample. All right. So we take our sample of 20 and we go about doing that, okay? And so what I've got, so I'm just going to simplify it again. We know that n was 20, wasn't it? 20, we're taking 20 deer. So it's x over 20 is greater than 1/4. And I'll just times both sides by 20. And I'll get x is greater than 20 over 4, which is 5. And that's the bit that I was saying you could probably take a shortcut. Because we're saying that the proportion of deer in my sample, we want it to be greater than 1/4. Well, what's 1/4 of 20? 1/4 of 20 is 5. So what we're saying is that we want x to be greater than 5. The number of deer in my sample, we want to be greater than 5. And if you can see the connection between that and that, then you've got it. You've got the concept, and that's all we're talking about here. Is that all p hat is x divided by n. Okay, in this case, x divided by 20. In this case, 5 divided by 20. So I hope that makes sense. And so once we've got the situation, once we've got this probability that x is greater than 5, then it actually becomes quite a simple problem. Now, all of what I was talking about here, all of this is all binomial, right? Because all you're saying is you've got a success. Is it a red token? Yes. Is it not a red token? It's not. It's a fail. And so that's a binomial. And we're doing in this first one, we did a sample size of 3. So we're doing 3 trials, all with probability of 1/4 of getting a success. So this is a binomial trial. And it's the same in our question here. We're doing 20 binomial trials, Bernoulli trials, essentially. We're doing it 20 times, and each time the probability of success is 1/5. So we can just think of this as a probability question, right? So we know that x is binomial. We're doing NP, so 20 trials. And what's the probability of success? It was 1/5. So that's my binomial distribution for x. Once I've got that, I can easily use the calculator to figure stuff out. All right. So therefore, probability that x is greater than 5 is equal to, and this is when it's time for the calculator. All right. So we go to our calculator and we go menu. We want probability. We want distributions. And what we've got here, this is binomial. And is it binomial PDF or CDF? PDF only does one value. CDF does a range of values. And here we want a range of values. Okay, so we go binomial CDF and we enter in the number of trials. What was the probability of success? 1/5, otherwise known as 0.2. Our lower bound, well, we want x to be greater than 5. It's not equal to 5. And because this is a discrete random variable, we need to start at 6. Okay, so we go 6. What's the upper bound? Well, the most that it could possibly be is 20 deer. Okay, so from 6 to 20 deer is what we're after with all those probabilities. And so our answer is 0. Let's call it, well, let's do 3 decimal places. So 0.196. And so that's how we do it. And so just looking back to this question now, gee, that 0.19 a bit random, a bit big. So that is the probability that the proportion of deer in my sample is greater than 1/4. So there's a 20% chance of that happening roughly. Okay, so hopefully that makes sense. We change from a p hat, change it into x, apply binomial your distribution, and calculate as per normal. Okay, hopefully that makes sense. Part B there, let's just knock that one over. What's the expected value of p hat? Well, the expected value of p hat, we just talked about it before, is equal to p, our proportion. Okay, so the value that we're expecting to get is p, and what was p? It was 1/5. Okay, which is 0.2. So that's what we're expecting to get in each sample. And lastly, what do we want? We want standard deviation, which is the square root of that. And standard deviation of p hat equals, and I've already forgotten the formula, p1 minus p square root over n, p1 minus p over n, and I might just go and totally put that in the calculator. So square root, oops, what happened there? Don't know what happened there. Square root, that's better. And what do we want? P, which is 0.2, times 0.8, 1 minus p, over size n. N was 20, and there's my answer. So standard deviation is 0.089. Okay, so hopefully that makes sense, and hopefully you understand what that sample proportion is, what it represents. If you get it, then you're sweet. But really, all you got to remember is that to change your p hat to x over n, and then calculate binomials with the distribution that you get. Hope that makes sense. I'll see you in the next video.